Thanks. Thank you.
I'm
Thank you, Dina.
serious.
Okay, so thank you, Mingyu, for presenting this time.
Just put the speaker
This
rate.
lady on comment that meant to
You can
talk about
yes,
Ivy to all
it's
of
good. It's good.
Today I'm going to present a work with Christy, the titled Safe Modular Deep Reinforcement Learning with Temporal Logic through Gaussian Process and Control Bar Functions. This is an extension of my previous work that published in the IAL. As an emerging research field, task planning is very important in the robotics. So in this work, we apply the formal language that has the rich expressivities for describe complex tasks for the robotic systems. And we consider the non-dynamic models and the continuous action state space. And we consider the task planning over infinite horizon because this is general requirement for the manufacturing robotic systems. And then we will ensure the safety during the learning for generate the optimal policies. Task planning involves many areas like autonomous vehicles need to obey different rules. The rules can be regarded as different tasks. And the manipulations need to handle different service. And the autonomous delivery robot needed to pick up the package, deliver it to the destinations, and go to the gas stations. And the similar task for the Mars exploration. So in technically, we will consider dynamic systems, a general continuous dynamic system with the disturbance functions DS. DS has two parts, which is D prime S and the Gaussian noise. And the FS, GS, D prime S are all locally Lipschitz continuous. And the D, yeah.
Does the prime indicate derivative or is it just a new name?
Just a new name.
Okay,
sorry,
thanks.
yeah, it's just new name. And the D prime S is unknown. And so we can model the interaction between the dynamic systems and the environment as a continuous labeled Markov diffusion process. So we assume that DS has a low complexity, which can be measured with the kernel Hilbert space. And then for the formal language, we use a linear temporal logic to define our high level tasks, which has the linear time, which can be expressed over the linear time properties with different Boolean operators and the temporal operators. For example, the next operator means the next state should be held. And the until operators, eventually operator, and always operator can be combined to express different tasks. And so in this case, we use a control bar function to define the safe properties. So control bar function is a barrier function that can be applied to the control systems to render the safe environment. And we introduce atomic propositions of the LTL to specify that the systems that satisfy the safe properties of the control bar functions. So we use always safe to express these properties. So our task can be like.
So for those of us who don't know linear temporal logic very well or the symbols, can you go a little more slowly? Like what does that box be safe mean?
Okay.
In the next line?
Oh, this safe is just a name, a notation.
Sure, it's a function, but I mean in the red box.
Oh, this
What is
one?
it? So it's box safe. What is that? How would I interpret that if I don't know linear temporal?
Oh, yeah, box represents the always operators, means always to be safe.
Okay, and then the next row, the next.
Next means this is conjunction, means at the same time we need to satisfy another formulas.
So we say always safe and
Always.
whatever the other function is.
Yes, right.
Okay,
So this is a general functions to express different other tasks.
and does the always course, sorry, what's the precedence and what's the scope of the always in that equation?
In
Is
that
it only on safe or is it on the entire conjunction?
entire conjunction,
Okay,
like for the entire time, the safe should be always whole. So always.
safe, but phi of G also always.
No, because the box is not in front of.
That's what I was asking.
So yeah.
It's not obvious to
should
people
not-
who don't do this stuff. They don't necessarily know.
Okay.
I'm one of those people.
Okay, it's a good question. So the assumption here is like we need to allow us to extract the safety of the dynamic system using the barrier functions. Otherwise, we cannot use the CBF to extract safety. So problem formulation is very straightforward. Like we consider CLMDP with the LTL formula in over the infinite horizon. So we want to find the control policy that generates a controller to satisfy the task with the maximum probability. At the same time, we need to guarantee the safe during the learning because learning is an interaction stuff process and which cannot be safe. And for example, like helicopter in the Mars provides the map to the Mars rover, but there exist complex terrains in the surface. So there exist disturbance functions for the dynamic systems so that we need to learn the optimal control policies.
Hey, sorry to slow you down, but will you tell us what's in the nominal dynamic system? What is FFS? What is G of S? What is, I know what D of S is now, I guess.
Oh, FS and GS is normal dynamic system like.
Why is it broken into two pieces?
Yeah, because FS is a part, do not involve
Affine.
control input. And GS is a part with the control input.
Okay.
It's called an affine system.
Yeah, of a control offline system.
Okay,
So our approach is first we design a dense reward based on the LTL instructions. And then we apply a modular DDPG algorithm, which is advanced deep reinforcement learning algorithm to find the optimal policy. And after that, our second part is to use the Gaussian process to approximate the disturbance functions. And then when we incorporate this estimation into the control bar functions to generate the safe controllers during the learning. And finally, we will provide the feedback to the neural network so that we can improve the exploration. So let's first explain the first part. First part is like for the LTL satisfaction, we always use the Automaton Theory, which means for each formula, we will translate the formula into a graph structure, which is we call that automaton. So the automaton is a graph, like it has accepting states. You can regard the accepting states as the destination of the graph. Like if you start from beginning to the destination, the task will be satisfied. And but for the model checking, there exist several automatic structures. And based on my literature review, the limited deterministic general LDGBA will be the best choice because it has more more destinations, which means we can assign a denser reward compared with others. So the LDGBA is a tuple structure that has a finite automatic states and the transition functions and a set of accepting states. So the accepting conditions require the sequence should intersect with all the accepting sets infinitely often so that the task will be satisfied. So we use a graph structure to measure the satisfactions of the LTL formula. That's the basic model checking theory.
can I pause you again? Sorry, everybody.
Yeah.
So I can think of the state space of this system as a big graph.
Yeah.
And there are several states within or several nodes within that graph that are goal states that if this and the system will start at any one of those nodes.
Yeah.
And it just, as long as it ends up in one of those states, then it's success.
Yes.
You're trying to find a controller that will determine what the transition function is to try to make sure that wherever it starts, it gets to one of those goal states.
Yes, correct. That's the
Okay.
graph theory. Yeah.
That's what?
That's the graph theory for
Oh.
the automaton theory.
Okay.
Okay. So as you example of the LDBA and LDGBA, like we can see in the figure A, LDBA, we have 3 destination nodes, which means we can assign denser rewards. And the second figure, we only have 1 destination node. So like if you start from the Q0 and intersect with all the accepting sets infinite open, the generated word sequence will satisfy the LTL formula exactly. This formula represented like we need to always eventually visit A and B. So if we have MDP can be regarded as another graph, and the automata can be regarded as the second graph. So the standard way to do the model checking is to product them so that we can find the controller in the environment, which is the CLMDP process. So this is a standard process to product them, like we can product the state, and we can add constraints to the transition functions. And in this case, we only use the product MDP to do the analyze. We do not construct it because it's impossible. The CLMDP is a continuous space, which means we have infinite states. So the product state will be the input to the neural network, which will be synthesized online. And the AMEC represents a bottom strong connected graph, which include all the accepting sets, which means if the agents enter into the AMEC, we can make sure that the task will be satisfied. So here is the problem of directly applying the LGGBA. Like figure A, we can regard it as a automata structure. Figure B is a MDP structure. And we do the product MDP process. We can see that the accepting condition require these states with infinity always visit circle A and circle 1 and circle 2, which is possible for a deterministic policy, because deterministic policy can only apply one actions for every state. So this is the issue. So in order to solve the issue, I designed a tracking function, which means we will keep tracking all the unvisited accepting sets online, so that we will give a feedback which one is not visited in each round. And we show that the designed ELDGBA has the same accepting language as the LDGBA, so that we can safely apply it into the model checking problem. And here is a reward design. Reward is directly assigned to the accepting states. And we verify that the expected return of the RL is exactly equal to the probability of entering into the AMEC, which means the expected return is exactly equal to the probability of task satisfaction. If we optimize it, we'll optimize the probability of the task satisfaction. So we build a bridge.
So are all these things I'm reading in all the math there, is that those are all expectations, or are those
oh yeah, these are expectation.
Okay.
Yeah. Because Markov decision process has a probability for the transitions.
Okay.
Yeah. But if we only assign the positive reward to the destination nodes, we have an issue of the sparse reward. So that I do a reward shipping process so that we can assign the reward to the other states, which will not influence the original optimal solutions. And the DDPG is an algorithm that based on assumption that there exists deterministic policies satisfy the goals. And we will optimize the loss functions and using the policy gradient method and do a soft update after each episode. However, directly apply the DDPG for the complex task. Because of the nonlinear regression, we cannot guarantee the performance. Like we cannot make sure that it can satisfy a task infinitely often, because DDPG has been only verified to achieve the go-to-go task. To solve the issues, we propose a modular DDPG, like we can decompose the task based on the automaton structures into subtasks. And each subtask, we will propose a new DDPG architectures to take care of it so that we can achieve the success rate to improve the performance. Okay, so right now we have the optimal policy to satisfy the task, but we cannot guarantee the safe during the learning. Next step is to guarantee this, to solve this problem. And we use a Gaussian process to estimate the disturbance functions. The Gaussian process, like we can have the sample data and use this update mathematic process. And we can have the mean and the covariance of the estimations. And final results, we have theoretically proved that this estimation has a theoretical probability bounded guarantee.
Can you explain what's in those plots? Green lines or red lines? What's going on there? What are
yeah, Red line means how to use the data to update the mean value of the estimation. And this one is represent how to use the training data to update the covariance of the estimation. And finally, we can use the mean value and the covariance to estimate, to bounded these estimations.
So there's a green line on top and a green line on bottom. That's like one standard deviation away from the red line or something?
Yes, standard deviation and the mean.
Okay, and then how did the red line get generated? Is that from some particular trial or a bunch of trials?
Yeah, a bunch of trials at the beginning.
Okay.
And compared with the neural network to estimate the disturbance functions, Gaussian process has the theoretical probabilistic guarantees. So that's the reason we want to use it, but we can also use neural network. And then we need to use the control bear functions with the Gaussian process to generate the safe controllers. And the standard control bear function form is this form. And we can see that it cannot handle the higher order control bear functions. So that in this work, we use exponential control bear functions like in this form. And here F prime is this E hat is the estimation using the Gaussian process. And finally, we can formulate a quadratic programming at each time steps so that we can propose a minimum perturbations for the RL controllers to generate the safe controllers. However, the issue is like safe controller is not generated based on the distribution of the actor neural network, because DDPG is the actor critic neural network. So that there's no connection between the safe controllers and the distributions. But this distribution is connected to the RL controllers. So that's the issues for the exploration, which means if we directly apply this safe learning process, it will influence the explorations with respect to the original optimal solutions. So that we improve it in the figure B, like we need to provide a feedback to the neural network using our control bear function information so that the neural network will recognize which RL controllers are safe, which are not safe. The detailed is like if the perturbation of the CBF is not equal to 0, which means the RL controller is unsafe, we will give a penalty. And then we will using the automaton state to indicate whether the RL controller to be safe or unsafe. If it's unsafe, the automaton state will switch to this unsafe component. And then we will apply this shift process into the reply buffer. And also we verify because our formula is in this form, which means optimal policy should satisfy the safe and optimal requirement, which means the optimal policy is a subset of the safe policy.
So Mingyu, can I ask a question?
Yeah.
So you are using the reward to softly guide the policy to do safe actions. Am I understanding this correctly?
Oh, yes, but we still need to give the input as the indicators to indicate this current state is unsafe.
So what do you do if you observe an unsafe state? So you correct this unsafe state with some actions not generated by the policy. Is that right?
No. Actually,
otherwise, the agent is still doing in the unsafe configuration, right?
No, because recall that for each, you can see here, each state has 3 components. S is the dynamics, Q is the automaton state. So our S state is always safe because we use the safe controllers for the executions, but we can change the Q state. Q state will not influence the actual implementation. So that Q state can be applied to indicate the RL controllers to be unsafe.
Okay, so even though the RL controller is unsafe, you have an extra layer to just do safe actions.
Yes, yes.
Okay.
Yes.
Thank you.
And here for the simulations, like we first consider the card pool, like the safe requires the pool should not should not falling down, and the card should always operating within this red boundaries. And this is a dynamic system with two orders degrees, so we need to use the exponential CBF. And we also have the parameters of the dynamic system has some errors, which is a nominal model, and we also add the Gaussian noise to the output.
Sorry, Mingyu, what are the yellow and green blocks?
Oh, yeah, sorry, I forgot to mention. Like the task requires the card 2 to always infinitely visit the green and the yellow box.
What do you mean, within the range?
What?
Within the range of these two boxes, or?
Yes. And I will show a video later.
And what are the red lines? I mean, while you have this picture here, you might as well tell us what it is.
Oh yeah, red lines is a safe boundary. Like the card should always operate within these red boundaries. This is one of the safe properties. And another safe property requires the bar should not fall down. So we have two error functions because, yeah. So here is the reward comparisons with the standard DDPG and the modular DDPG with safe or without safe. And here we show the boundary, the maximum angles, maximum positions for the bar and the cards during the learning. And here we show the same parameters during the evaluations. We can see that if the red line, if we add the CBF, it will not exceed the boundaries.
So there's orange and there's blue, and then there's the red line in that particular plot. So can you say what the orange line is, what the blue line is? Because the orange line does go above the red one.
Yeah, orange line means the modular without safe.
And it's motion of the system?
Yeah.
What is that plot? I can't read the axes.
Oh, it's the position.
Position versus time?
Yeah, position versus episode.
Okay.
Maximum position during the episode for each episode. Yeah.
All right. So the orange without the special control fails, and
Yes.
blue never exceeds that red line. So that's
Yes.
the point.
Yes.
Okay.
And here we also test it in the pendulum, like the safe requires the pendulum not to exceed this red boundaries during the learning. And the task requires the pendulum always visits this two green color infinitely often. And here we also show the similar things. And here we can see the rewards, the blue rewards with the guiding process. It converges fast. It converts fast. And here we show that because the policy is a sub policy of safe policies, which means finally we can remove the CBF, the safe filters, because the policy has become safe. So this CBF perturbation will decay to the zero. And finally, we use a car model, the double integer car model to test our algorithm. Like for the first task, the mobile robot should visit these 5 spots and avoid obstacles. And for the Mars service, we test it also in the Mars service, which is the image pixel-based learning. And the task requires the robot to visit these 12 spots infinitely often and always avoid enter into the craters marked with this red circle. And we compare the reward. Like we can also see that the blue one converges fast. And finally, I show videos for the learning. Yeah, we can. Oh, sorry. We can see here the red, the left represents the unsafe learning process, and the right represents safe learning process with the CBF. And here is the optimal policy, like the car 2 will visit this regions infinitely often.
Are you showing the same thing in a loop, or was it supposed to go back and forth between those regions over and over?
Yeah, over. It's
Okay.
supposed to do.
So that was
because-
one run. It wasn't a looping thing. Yeah.
Yeah. This is a task expression. And then we show that this is unsafe and this is safe during the learning. Like you can see that this will not exceed the red boundary. And finally, we got the safe policies.
So Mingyu, so for this particular example, the carpool example, so what do you do if the controller output is unsafe?
Yeah, if your IR is unsafe, I will use a CBF to find a safe controllers for the executions. And at the same time, because the input to the neural network has the automated state, I will change the automated state into the unsafe automated state to indicate the original RL controller is unsafe.
Okay, so what do you mean by finding a safe controller? Do you mean you have a analytically derived controller to do that, or?
Yeah, because we solve it in the quadratic programming using the control bear function. Oh yeah, here I need to probably shoot back. Like here, because theoretically, if we can solve the controller that satisfies these equations, we can guarantee the safe set is forward invariant. That's the control bear function theory.
But my question is, my point is, if we can analytically find a controller, then why do we need to learn another controller?
Yeah, because the dynamic system is unknown. It's very hard to find the dynamic in the continuous space solve these complex tasks.
Then how do you derive this controller, the safe controller? How do you guarantee the safe controller is the right one to use here?
Sorry, I don't understand.
So to my understanding, you have.
His question is that I think you already have the model of the pendulum, right? The pendulum. On
Yeah.
the part, you already have the model from the physics of the problem.
Yeah, we have estimations for the models.
You can find. The only unknown part are the parameters, but the structure of the system is known because it follows the physics.
Yeah.
Maybe the mass is not known. Maybe the length is not known.
Yes.
And is all that captured in the first line of the such that box there?
Yes, it's
So the L sub F1 super TB HS blah blah, all that greater than or equals 0, that's the dynamic model of, or that's just a
That's a
constraint
constraint.
on the.
But that's a constraint.
it's the constraints.
that's the
It's the
Lyapunov.
CBF constraints, and L
Okay.
represents the lead derivative.
But you have the model, and what you're saying is, since you have the model, it's a parametric model, but with that model, I suppose you can get a parametric solution that would be an optimal or a safe controller.
Yeah,
I think that's kind of, and so if you can get a safe controller from the model, why do you have to learn anything? Why don't you just use that safe controller?
Because safe controller cannot satisfy the LTL task. Our task has two parts, the general task and the safe task. So you also need to satisfy the general task, except the safe task.
So if there's no constraint, you would have a controller. But the moment that you put the constraint, that explicit form for the feedback would go away. So the feedback form is not going to be that nice form anymore.
And was
Because
that
there are
somewhere in your model earlier in your slides? Like the part that was known and the part that was caused by constraints? Because I didn't catch that as you were going through the beginning.
Okay, first I need to point out this is a general form. So the safe controller cannot satisfy the 5G.
Okay, so when you add 5G, that's when you need to do the learning.
Yes, right.
Okay, well okay, all right, good, thank you.
Okay.
Also, maybe to point out, Mingyu, is that the control barrier function approach is actually a way to adapt the output of a controller to keep it safe. So if you had your controller that does maybe something else, you usually put this control barrier functions on top of it to ensure it's safe. The problem is that, and why Mingyu is doing this in this way into the learning phase and integrating the safety into the learning is you don't have a guarantee that changing your output from a controller that is supposed to do something like driving you down the road and applying a safety on it will actually accomplish the original goal. So think of here a stalled car in front of you. The safe thing to do is to just stop and wait. But if the car in front of you never moves, then you're never going to your destination. So learning how to go around that while keeping safe is what this is supposed to do.
And yeah, after I finish the slides, we can go back. Like here, like we can see that in this environment, our algorithm can apply to the infinite horizon task and the finite horizon task with a very stable, excellent performance, even though we use a neural network. So the most contribution in the work is that I propose a modular DDPG architecture. And I finally compare the safety rates for during the learning process. And we can see that if we have the safe learning with the guiding, we can have a very higher percent to guarantee the safe. Because the control by function may have the infeasible solutions. So sometimes even though you use it, you cannot guarantee the safe. So that's the reason this is not 100%.
So what are the differences between the blue, green, and orange bars?
Oh,
One says safe on something, one says
oh,
safe off, and the other says modular. So I wanted to map those into what you actually did.
okay. The orange represents algorithm only applies the modular architecture without safe.
Okay.
And the green one represents the safe, but without the guiding. Like I propose a feedback to improve the exploration, right? So the green one represents without the exploration improvement. The performance will be bad
And the
because
exploration is of this giant state space.
no, learning process is a exploration versus exploitation process.
Right.
So we have to explore and then we learn. Right?
Okay. And you're not exploring in that state space, you're exploring in some other space.
During the learning.
During the learning.
Right, but what
Yeah.
space is that you're exploring, I guess, is
Yeah.
what. Which space? The space of what is being explored?
The space of the CLMDP,
Okay.
the interaction between dynamics and the environment.
LMDP means what?
The continuous labeled MDP. That's the state. So here is the success rate. After I learned the optimal policies, I run 200 runs and I compare like the percent of the algorithm satisfy the task exactly. I compared with using the standard DDPG with the safe. So we can see that because the nonlinear regression properties like this directly applied has a very poor performance, especially for the complex task over the infinite horizon. Yeah, summary, like because we have disturbance noise, the CLMDP is actually has the unknown transitions. That's the reason we want to use the learning. And yeah, and here is a summary. And the future work, I will consider the multi-agent safe learning, extend this work. And then I will consider the large-scale complex environment. Yeah, that's it.
I think Wang Yi has a
Yeah.
question.
I have a question. Oh yeah. You don't go either. So very interesting talking. I do have a question. When I say that one of your tasks is going to visit some of locations infinite many times, right?
Yes.
So one is keeping safe, one is meeting your task infinite many times. How do validate if you have learned to visit them infinite many times?
Okay,
Yeah.
that's a good question. Like, in the simulations, like for each round, after we finish the visit all the accepting set, I will count the numbers of the round. Like I finish the task once, and like I give in the specific rounds for during the testings, the task should visit. Like I compute the average time, like the optimal policy should complete the task, average number of the rounds, and I compare it with different algorithms.
Okay. So when you say that your learn algorithm, your learn controller will visit that like infinite many times. So
yeah.
Do you have a guarantee on that, or so how do you validate if this is true or not? How do you validate if your controller can do that, or it just do it 1,000 times, but at 1,001 it will fail?
Oh yeah,
Okay.
That's a good question because this is neural network. I feel like we cannot guarantee that. We can guarantee it in the limit.
Not yet.
Yeah, not yet. Yeah. Because
I mean,
yeah, it's
there are
not.
some works that they have started to prove things about the neural network. So you can use the I mean, like in some problems. So my question was this: can you guarantee? I mean, what are the conditions that under which this is going to work? What are the conditions that you can derive on trainable weights, on your dynamics, on your constraints, such that you can guarantee that if one solves this problem, then it's going to get the safe
Oh yes,
network policy.
yes. Like future work, I will also consider add another modules to like if the neural network has some undesired behaviors, how can I correct it based on our objective? Yeah, that's a challenging problem.
So would this work for any system, for any
Yes.
affine system?
Uh,
Because I didn't see any condition that would classify the systems. So if I put a non-smooth system, would this still work for a non-smooth system? If I put a non-holonomic system, would it still work for that system? I mean, what are the class of systems that this can handle?
Yes, you're right. For the non-smooth systems, like the working robots, something like the hybrid, there's some states with some jump. I think,
Bouncing.
yeah, I think it depends on the Bellman update because the RL is based on the Bellman update. It depends on if all the states can be connected based on the Bellman update to optimize the expected return.
So
So
would you be able to say that what are the conditions on FNG? So should your system follow some properties or have some conditions for which that condition holds?
right now, I just assume they are all locally Lipschitz continuous.
The Lipschitz continuous, and also you take their Lie derivatives.
Yes, Lie
So you assume that
derivative. So,
they're smooth enough.
oh yeah, smooth enough.
Smooth
Lie
enough,
derivative. Yeah, because this is kind of assumptions for the control bar functions, so I didn't highlight it in our. It's actually a tool for me.
controllable system, right?
Yeah, controllable systems. The big assumption here is like we need to model the safe issue into the barrier functions. So if we consider a general environment, it's very hard to manually construct a barrier functions because our environment has different shape. So currently there are some ways to learn the barrier functions from the data. Yeah, and I'm also investigating this kind of directions, how to apply it into work, like apply the algorithm into the autonomous driving.
So you mentioned barrier functions, and so they could just be another neural network that represents some barrier function.
Yeah.
Doesn't have to be.
They call that neural network, neural barrier certificate. Yeah.
So you have read the paper by Victor Preciado,
Yes.
learning the barrier functions.
Yes.
So if you put this, so how this work is different from that?
Currently,
I mean, they don't have the temporal logic part, but if you just focus on the barrier function part.
oh yeah, I think I do not have enough contribution on that part.
Okay,
My
that's fine. I mean, I'm just trying to.
Yeah. And our future work, like if we consider a multi-agent system and the barrier functions for the neighbor agent is very hard to manually construct. That's the reason I want to use a neural network, barrier functions, versions. Yeah.
We should talk more then.
Oh, yeah, sure.
Okay, good.
Could you please give an example of how you obtain the LDGBA, right? When
Oh,
slide
LDGBA, yeah.
So for the same specification, how do we make sure that we have multiple final states?
Oh, LDGB, I translated using a tool. Yeah, I forgot to mention because I think most people are not focused on formal method. So
Yeah, sorry, I was just wondering how we end up. Yeah, slide 10.
yeah, there's an online open software
Okay.
using the C language, so we can translate it directly from a formula to an automated structures. But then I will combine it with the tracking frontier function to construct the embedded LDGB because I said the LDGB cannot work.
And sorry, I have one more question. So when you explained the approach for having modular DDPG structure, so in that case, is it happening in sequence that like the output policy of one module is going as input?
Yeah. The modular. For example, this automata requires the robot visits AB T1, T2, T3. Anytime when the T1 is visited, the automated state will switch to the Q1, right? And the DDPG architecture will directly select to this one here. So it's based on the automated state. We use the automated state to track which DDPG we wanted to use at current steps.
So I have one other question if no one else does. Early in your talk, you said something about not being able to visit all of the state space that's relevant. And you said, and then later when you were answering one of my other questions, you mentioned exploitation versus exploration, which is a standard thing in motion planning and robotics, I guess, where without all the dynamics and the temporal logic, and if you just go to very simple motion planning and robotics,
Yeah.
that's the same situation, that the configuration space is high dimensional. There's many places to visit. You're never going to visit them all while you try to solve your motion planning problem. And so you try to do some combination of, or maybe back and forth between exploitation and
Yeah.
so this space that is the one that you're exploring and exploiting, that's the CLMDP space. Or what I guess what I'm trying to do is, like, for a robot arm, I know there's a bunch of joint angles.
Yeah.
And when the space that I'm searching for motion planning is the space of all those joint angles.
Yeah.
I'd like to know what are the parameters of the space that you're working in? I don't quite get that. It could be inputs, it could be joint angles, it could be how far the pendulum is. I don't know. What is that space?
Is
Okay.
Rn, or it is a combination of
Actually,
Rn with some
It's
some
Rn cross
automaton.
something else?
Yeah, the cross with automaton space.
yeah.
And so then the parameters are, the Rn would be like joint angles and such of a robot,
Yes.
and then the automaton space would
This would be
be,
the Boolean variables probably.
Yeah, putting very.
okay, well, that was
Space of-
one of the pieces that I couldn't quite see.
Yeah.
So you
What is-
never can work with the whole space, you just have to explore and exploit, right?
Yeah. It depends on how you define the environment state with your dynamics.
And then will you get a different, I guess you'll get a different controller
Yes, right.
depending on how you do your searching.
Yes, right. Here I just apply the position of the robot into the space, but you can apply the angles and the computation
So
of them.
in this problem, you didn't include velocity.
Yeah,
in
I
this
just
Rn,
I just included the positions.
okay.
So I would restate, what is the underlying state space of your system or your problem? If I just have x dot is ax plus bu is Rn. X is in Rn. But in here you have x and also you have some constraints.
Yeah.
So what is your state space? What is the underlying state space of your problem? I think that is important to know.
Underlying state space. What's that?
Is it the product MDP?
So your system lives in some space. So if I don't have the constraints is Rn, but now I have some sort of constraint.
Yeah.
So that would define a new space.
Yeah.
If it was a holonomic or like a non-holonomic system, it would be a manifold because I would have the geometric constraints.
If they're equality constraints.
Yeah. And then for the arm, I think it's going to be the SO3 or SO.
For SE3, for a
SE3.
single arm or something
Yeah.
like that.
So then cross of that with all the joints. So we would like to know that what is the underlying state space that you're trying to work in or your system lives in.
Oh yeah, the underlying space I think it should obey the constraints of the dynamics. So yeah, it original has a dynamic constraints.
So it's positions and
Yeah, positions.
velocities,
Yes.
and that's the underlying state space. It's like the product of SE3 and
I got your question. It should be the space that we can label it, because we call that a continuous labeled MDP, which means you need to label it, and you use a label to express your linear temporal logic. So it should be the space that you can label it, and you can use it to express the formal language.
So if I recall from the Automaton Theory, which I took back in 2004 with that French, so what was the French professor with Jean Gallier
oh, that guy.
back in 2000. So I remember that a state space of an automaton was the all possible words that you can make. Right?
Yeah, yes, right.
It was long time ago.
Yes, right.
15 years ago. So is that cross with Rn? Is that something like that with?
Yeah, the state cross with product cross with the dynamic state.
Right. The
Product MDP.
Yeah, cross with the MDP
I think
state.
to Christy, you may want to
Yeah.
make a comment here.
Right, I was going to say that the set of all words is the language of the
Yeah, the language, yeah.
the language. The state space of the automaton itself is just the states in the graph. So it's a discrete, finite, usually state space. And so the cross product. I mean, the space that you're asking, it really depends on the system. So if we have, let's say, a car, then we'll have, if we look at the state space of the car, it'll be potentially planar cars will be SE2 plus the velocities. And if we go to full dynamic model, it'll be also two accelerations. But I think what Mingyu did here was with the carpool and the, is basically more in a generalized the configuration space of the system plus the generalized velocities. Then that is the MDP, and the search space itself is going to be crossed with the automata state. But because it's modular, you don't need to take, you don't, and because that second space that we do cross with is finite, you can split it up and solve the problem separately for each of those modes, so that you don't have to embed into your problem the automaton itself. And so that's one of the things. It also is kind of like a factored approach to the learning problem, where we factored out the automata state from the search space.
Thank you.
Thanks, Christy.
Thank you so much.
So, Mingyu, I have a related question. So it seems the automaton states are very important to your algorithm, because you need to, based on that, to select different RL modules, right?
Yes.
To my understanding, currently all those states were manually labeled, right?
Yes.
Yeah. So a question from me is it possible to let machine learning to handle this labeling by itself? Right? Because if we want an agent to freely explore a space and do whatever it wants, to produce a more general intelligence, right? So that you can do abstraction of the system, extract those states, automaton states, and then perform, decide the RL module by itself. It will be more autonomous.
Yeah, actually, the abstraction process related to the unknown dynamics or unknown environment or known environment. In this case, I consider the known environment,
Right.
so that we can label it directly. But if the environment is unknown, you need to use some other abstraction techniques to get it. Yeah, that's another story. So currently learning for the unknown dynamics, unknown environment is quite hard. And you need to explore the environment at the same time learn the controllers.
Right, yeah. But if you can do that, then it's a very nice contribution.
Oh, yes, yeah.
So, Jinda, maybe I can jump in. We have some work where from data, we learn formulae or rules, but the symbols themselves that we use, the labels, if you want, those are still given to us to some regard. Learning symbols themselves equates to kind of like learning a semantic context. And so that's very difficult to do. And it's been an open problem for a really long time. That would be very complicated to do.
Yeah, I'm asking because I tried to use a modular learning of manipulation tasks. Basically, the manipulation tasks, we can simply divide the stages into different sub modules. Like if we want to push an object, we can easily divide that into a reaching phase and a pushing phase, right? So there are two phases we can manually label, and we can train different controllers to achieve different goals. Yeah, but during that course, I find if a robot can just learn the labeling and the controlling part by itself, then it'll be amazing.
Right. So what you're talking about is maybe to quantify with what we're saying is you do know the symbols because you say you have pushing and you have other actions.
Reaching.
So what you're enriching. So over the time series that you get from your from the data, what you're doing is a segmentation and labeling those segments. And so that is something that we're also looking into and figuring out how to do properly while also learning rules, but learning the actual symbols, the fact that you know about reaching and you know about pushing itself, that's the hard part to extrapolate to.
Yeah, I understand that. We human beings are so good at this. Why robots can't?
That's the problem, right? General AI.
Right.
Good.
Thank you.
Yeah, I guess that's it.
All right, thank you again.
Yeah, thank you.
What's the name?
Do we have anything?
For an automaton book. He's an MIT professor, Michael Sipser.
I think that we can stop recording.
Yeah, we can probably stop recording first.